Welcome to Brain Vision.
Okay, so doing chapter 37, problem 50. So it says calculate the de Broglie wavelength of an electron in a TV picture tube if it's accelerated by a potential difference of 33,000 volts. Is it relativistic? How does its wavelength compare to the size of the neck of the tube, which is typically 5 centimeters? Do we have to worry about diffraction problems blurring our picture on the screen? Okay, so the final kinetic energy is equal to the negative change in potential energy as it passes through the potential difference. So we can write kinetic energy final is given as the change in potential energy, which is negative Q delta V, or the potential difference. So this is delta V here. And this becomes 1e times 33 times 10 to the 3 electron volts. Sorry, that's just volts. We see that's 1e times that, so this becomes 33,000 electron volts as the final kinetic energy. So how does this compare to the rest energy of an electron? Well, the rest energy is given by 0.51 mega electron volts. So that means kinetic energy of the electron over the rest energy is greater than 0.01. And because of that, we take it as relativistic. So this means if the kinetic energy is greater than roughly 1% of the rest energy, then we say it's relativistic. And it is. Right here, we're about, what is this? We have 33,000 electron volts over 511,000 electron volts. So 33 over 500, about 3 over 50, about 6%. Cool. So now we're going to use equation 3613, which lets us determine the momentum, and then 37.5 will let us get the wavelength. So first of all, we know that E squared is given by K plus MC squared, because this is just all of the energy here. There is only kinetic plus the rest energy. There's no potential or anything. And this is equal to P squared C squared plus M squared C to the 4th. So now let's rearrange this, and we see that P is now the square root of K squared plus 2K MC all over C. Well, equation 37.5 gives us that lambda is just H over P. So this is now HC over square root of K squared plus 2K MC. Cool. So let's plug this in. So this is 1240 EV nanometers. It's our little handy shortcut for HC. And now we have the square root of 33 times 10 to the 3 electron volts squared plus, sorry, this is MC squared down here. I missed that somewhere. Plus 2 times 33 times 10 to the 3 electron volts. And then we have MC squared, which is the rest energy of our electron, which is 511 times 10 to the 3 electron volts. Okay, so we should have everything in electron volts squared on bottom, and then square rooted to electron volts, and these cancel, leaving us our answer in nanometers. So we plug everything in our calculator, and this comes out to being about 0.0066 nanometers is our de Broglie wavelength. Awesome. And now, how does this compare to the size of the neck? Well, the size of the neck is roughly 5 centimeters, so this is much, 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 much smaller. 5 centimeters, which means no diffraction effects, or whatever diffraction effects are going to be negligible. Awesome.